Kurinji Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
Kurinji Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss about the important concept from this chapter, that is Bernoulli's principle. Okay, I didn't write the heading there, but I am saying that is what Bernoulli's principle, right? Bernoulli's theorem or Bernoulli's principle, right? Okay, see here. See, actually, in case of fluids, that is what in case of fluid dynamics, when the fluids are in motion, right? This is the relation, this is the theorem which is given, which is going to derived, right, by Bernoulli, a famous scientist, right, Bernoulli. Regarding the fluids when which are in motion, right, see what is the pressure energy and what is the kinetic energy and what is the potential energy. So regarding the earth, that is what the gravitational potential energy, and regarding the motion, that is what the kinetic energy, and regarding the pressure difference, you know very well when a fluid is going to move from one place to another place, right, that is what there itself the situation, the things which are present there causes pressure difference, right, causes pressure difference, okay, that is right, okay. Now see here, consider a fluid moving in a pipe, consider a fluid moving in a pipe of varying cross-sectional area. So this is the pipe, there is a change in cross-sectional area, no? Okay. And you know, one more point I want to say actually here, that is what fluid flow is a complex phenomenon. Actually, fluid flow is a complex phenomenon, but we can obtain some useful properties for steady or streamlined flows. That's what we discussed in our previous class using the law of conservation of energy, using the law of conservation of energy, okay, right. See, now he is asking to consider a fluid moving in a pipe, it is a pipe moving in a pipe of varying cross-sectional area, of changing or varying cross-sectional area, right. Here, you know, this is the pipe, this is what A1, A2 means area of cross-section, P1, P2 means pressure difference, and V1 is the velocity at this point, V2 is the velocity at this point, delta T is the time in which the fluid is going to flow from here to there, right. So when we have velocity and time, this is the displacement covered by the fluid in that instant of time, that is what delta T. So the displacement is V1 into delta T, here the displacement is V2 into delta T, right. It is the height of this pipe, the end BC, that is H1 from ground, and it is from H2 from ground, and it is the part BC, it is the part DE. This is all about the fluid flowing in a pipe of different cross-sectional area. Here it is A1, here it is A2. So this picture we have to understand clearly, so that you can understand the derivation part, right. Because of this pipe be at varying heights as shown in the figure, okay. Now you just suppose that an incompressible fluid means what? So the free flow causing any greater change in pressure, right. So negligible amount of change in compression, that is what there is no compression, almost a negligible amount of compression had taken place regarding the flow of fluid, regarding the flow of fluid, right? That is, its velocity must change as a consequence of equation of continuity. That is what kinetic energy. See, here the velocity is v1, here the velocity is v2. A force is required to produce this acceleration, right? A force is required to produce this acceleration. When there is a change in velocity, automatically you can say that there is some acceleration, no? Because acceleration is the change in velocity divided by change in time. Okay, that's why. So when there is a change in velocity, you can say that there is a acceleration. You can say that the fluid is accelerating. Fluid is accelerating. That's what we can say, right? Okay. The force is required to produce this acceleration, which is caused by the fluid surrounding it. Which is caused by the fluid surrounding it. The pressure must be different in different regions. See, here the pressure is P1, here the pressure is P2, right? So there is a difference in pressure in different regions. Generally, Bernoulli's equation is an expression which relates pressure difference between 2 points in a pipe to both velocity changes. Velocity changes means kinetic energy, right? Height changes, elevation changes means potential energy changes. So Bernoulli's equation is a general expression that relates the pressure difference between 2 points in a pipe to both velocity changes and elevation changes, right? So the kinetic energy changes and the potential energy changes. Right, now see here, that is what consider the flow at two regions. One is BC region, another one is DE region. Consider the fluid initially lying between B and D. First you consider between B and D, then you consider between C and E, right? In an infinitesimal time, that is what delta T, the fluid would have moved from here to somewhere. See, whatever it may be the point we are going to assume. See, when the fluid is in the region at BC, here the speed is V1, or velocity is V1. Here, that is what V2. So what can we say? The fluid would have moved. Suppose V1 is the speed at B and V2 is the speed at D. Then fluid initially at B has moved a distance V1 into delta T to C. That is what V1 into delta T is small enough to assume constant cross section along BC, right? It is what the small consideration. In the same interval delta T, the fluid initially at D moves to E, a distance equal to V2 into delta T. This is only V2 into delta T. This is only V1 into delta T, right? This part only V1 into delta T. This part is V2 into delta T. Pressures P1 and P2 act as shown on the plane faces of areas A1 and A2, binding the two regions. This is what one region, this is what another region. Now, the work done on the fluid at left end BC is, see, I have written here clearly, see the work done, you know the formula, that is what W is equal to F into S, right? You know the formula, that is what P is equal to F by A. From these two formulas, W is equal to F into S and P is equal to F by A. When P is equal to F by A, F is equal to PA, no? So in place of force, you can write pressure into area. Similarly, in case of displacement, we can write velocity into time. Am I right or not? Because velocity is equal to displacement by time. Displacement is equal to velocity into time. So with the help of these three formulas, so remember, one is W is equal to F into S, next P is equal to F by A, next V is equal to S by T. That is what velocity is equal to displacement by time. By using these three relations, these three formulas, we are writing this one. That is, the work done on the fluid at left end BC is W1 is equal to P1 A1 V1 into delta T. Right. See, that is equal to P1 into delta V. That is equal to P1 into delta V. So, what is the delta V? That is, delta V is a volume. Since the same volume delta V passes through both the regions, that is we discussed in previous class, equation of continuity, rate of flow is constant, AV is equal constant. That's what we are using here. So, because of the flowing same volume, because of the same volume of fluid passing through both the regions, what can we write? The work done by the fluid at the other end, the work done on the fluid at right end, okay, other end or right end, because left end, right end. D, that is W2 is equal to P2 A2 V2 into delta T. Right. So, this is what we are going to replace with delta V, P2 into delta V. W2 is equal to P2 into del V. Right. Now, part of this work goes into changing the kinetic energy of the fluid, and certain other part goes into changing the gravitational potential energy. So, law of conservation of energy is valid everywhere in the universe. So, whatever the energy is there, that is according to the situation which is present here, that is the sum of pressure energy, kinetic energy and gravitational potential energy. Okay, right. Suppose if the density of the fluid is rho and delta m is equal to, that is mass, no? So, density is equal to mass by volume. Density is equal to mass by volume. Mass is equal to density into volume. Density is equal to mass by volume. Mass is equal to density into volume. So, volume means you can write this one. So that if the density of the fluid is rho and delta m is equal to rho into A1 V1 delta T, rho into A1 V1 delta T, that is equal to rho into delta V, that is equal to rho into delta V is the mass passing through the pipe, in time delta T. Then what is the change in gravitational potential energy? That is here. See this, delta U is equal to rho into G into delta V into H2 minus H1. Actually, it is mgh, ma. See, in place of m, we have taken this one, no? Rho into A1 into V1 into delta T into H2 minus H1. So, in place of this A1 V1 delta T, we have written delta V, that is the volume of the fluid. That is the volume of the fluid moving from one place to another place of the pipe, right? That's what we have to keep in mind. You can see on the board. So, that is total work done on the fluid, W1 minus W2 is equal to P1 minus P2 into delta V. After that, you can also see the density of the fluid is rho and delta m. That's what I already told you. Rho into A1 V1 delta T, that is equal to rho into delta V, which is the mass passing through the pipe in time delta T. Then change in gravitational potential energy is delta U is equal to rho into small g into delta V into H2 minus H1, right? Okay. The change in its kinetic energy, this is what the change in gravitational potential energy, but the change in its kinetic energy is delta k, okay, k is equal to, that is half mv square formula, no? So, half is okay, V2 square minus V1 square also okay. Just in place of mass, density is equal to mass by volume, no? Mass is equal to density into volume. So rho into delta V. Rho into delta V. That's what we can write. Now, by using work energy theorem, P1 minus P2 into delta V is equal to 1 by 2 rho delta V into V2 square minus V1 square plus rho G delta V into H2 minus H1. Right, pressure energy, kinetic energy, gravitational potential energy. Okay, right. Mathematically, on both the sides of equation, we have delta V, delta V, delta V. Right? You can cancel, no? Right. So the resultant one, P1 minus P2 is equal to 1 by 2 rho V2 square minus V1 square plus rho G into H2 minus H1. Now, next one ma, P1 plus half rho into V1 square, P1 plus half rho into V1 square plus rho G H1 plus rho G H1. It is what P1, it is what half rho into V2 square minus half rho into V1 square now. So this minus half rho into V1 square will come this side, that is P1 plus half rho into V1 square plus rho G H1 plus rho G H1 is equal to P2 plus half rho into V2 square plus rho G H2. Just I am telling mathematically, right? Now, when it is correct, you can write the general expression, that is P plus half rho V square, P plus half rho V square plus rho G H is equal to constant. This is what pressure energy, kinetic energy and potential energy, gravitational potential energy. So regarding the nature of flow, that is non-viscous, incompressible and steady. For a non-viscous, incompressible and steady flow, the sum of potential energy, kinetic energy and gravitational energy is constant. Okay, right. Now, in words, because it is a mathematical statement, in words what can we say? The Bernoulli theorem relation may be stated as follows. That is what, as we move the statement of Bernoulli theorem in terms of words, that you listen carefully. Along a streamline, the sum of the pressure, the kinetic energy per unit volume and the potential energy per unit volume remains constant. The kinetic energy per unit volume and the potential energy per unit volume remains constant. Right? I will repeat once again the statement. Please keep in mind. As we move along a streamline, okay, I can say that for a streamline flow of fluid, the sum of pressure, the kinetic energy per unit volume, that is rho V square by 2, and the potential energy per unit volume remains constant. Okay, that is right. Next, note that, see, in this situation, note that in applying the energy conservation principle, there is an assumption. What is the assumption? That no energy is lost due to friction. That's what we assumed. But what is the fact? When fluids flow, definitely some energy does get lost due to the internal friction. Even when you are going to take some water in a water bottle made up of plastic, right? So when you are trying to pour down the water, there definitely, no doubt at all, definitely the fluid molecules will try to oppose by the surface of the plastic. I am talking about inner surface. Because of that only, when there are little drops like 1 or 2 drops. If you try to pour down, these 2 drops will take a lot of time to come to down. That's what we experienced many times when you are trying to drink water, when the water is very, very, very less in quantity. That's why we cannot say that there is zero friction, but our assumption is there is no friction or zero friction. So what is the fact? When fluids flow, some energy does get lost due to the internal friction. This internal friction arises due to the fact that in a fluid flow, the different layers of the fluid flow with different velocities. Due to the fact that in a fluid flow, the different layers of the fluid flow with different velocities. Stop. These layers exert frictional forces. These layers exert frictional forces on each other. These layers exert frictional forces on each other, resulting in a loss of energy. Resulting in a loss of energy. And that exerting of frictional force on one of the layer by other layer is simply called as viscous force. The nature of fluid is called as viscosity, and the name of the force is viscous force. Right? That is the important one that we will discuss in our coming classes in detail. What is the viscosity, how to calculate the viscosity, and what is the viscous force, etc. Okay? Right. The last kinetic energy, the loss of kinetic energy of the fluid gets converted into heat energy, so that the Bernoulli's equation ideally applies to fluids with zero viscosity or non-viscous fluids. And there is also another restriction. That's what starting of this class I told you. That is what the fluid must be incompressible, as the elastic energy of the fluid is also not taken into consideration. But in practice, it has a large number of useful applications and can help explain a wide variety of phenomena for low viscosity, incompressible fluid. That is the great importance of Bernoulli's theorem. Okay, now Bernoulli's equation also does not hold for non-steady or turbulent flows, because in that situation, velocity and pressure are constantly fluctuating in time. Velocity and pressure are constantly fluctuating in time. Okay. Now, when a fluid is at rest, its velocity is zero everywhere. When fluid is at rest, its velocity is zero at everywhere. This is the situation we come across in a reservoir, right? In a reservoir. So where because of its velocity is zero, the fluid is at rest. Now, Bernoulli's equation becomes P1 plus rho g H1 is equal to P2 plus rho g H2. P1 plus rho g H1 is equal to P2 plus rho g H2. That is what when the fluid is at rest. From this equation, mathematically you can write this one now. That is P1 minus P2 is equal to rho g into H2 minus H1. P1 minus P2 is equal to rho g into H2 minus H1. Right? This is the pressure difference, and it is the difference in potential energy, the gravitational potential energy. Right? So the pressure difference or the difference in pressure energy is equal to the difference in pressure is equal to the difference in position or elevation or height. But we have to talk about energy. This is what pressure energy, and this is what gravitational potential energy. Okay, right, when the fluid is at rest. Okay. So in this class we discussed Bernoulli's principle. Bernoulli's principle, that is what we can also call it as Bernoulli's theorem. So in case of non-viscous incompressible fluid, this statement is valid, and this statement is highly useful in our day-to-day life when we are going to study the properties of fluids. When we are going to study the properties of fluids. Okay, right. So in the next class we will continue with the next continuation topic, that is speed of efflux. You can also call it as Torricelli's law. Thank you.